Now we can get back to reconstruction again. Remember, we're trying to go from sinograms to images, and initially we're dealing with that in 2D. So let's take a look at one of the early examples of that for PET data. So this wasn't the first example of a direct reconstruction, but for PET, it's probably close to being the first real example. This is a representation of the method of Hagstrom et al., published in 2019. And what they do is they take a sinogram, a 2D sinogram, and they run it through a convolutional encoder into a feature space. So that's exactly the same process I've been talking about before. Here I'm spelling out some of the details of what they use, different convolution kernel sizes, batch normalization, relu activation. And then once they've encoded that sinogram into this rich feature space, now with very low spatial dimensions, but a large number of features, got 1,024 features there, feature maps. So in fact, these should actually be looking fatter and fatter and fatter, but obviously it's not very efficient on the slide to show that. Once you've encoded into that space, you can then decode back to your desired domain, which would be an image space representation of that latent information. And this is done, as implied, by doing the opposite of this downsampling. So downsampling, just to emphasize, that can be done by max pooling, or it can be done by strided convolution, where you just skip pixels with your convolution kernel, and that means your output size is going to be reduced in size. Upsampling, you can either do a convolution, or you can do basically bilinear interpolation, for example, in 2D. But these are standard methods that will be available in your deep learning, whatever your favorite deep learning package is, whether it's PyTorch or TensorFlow, for example. So what they did then was train up this convolutional encoder, decoder, and of course, just to point out two things, they had to use a huge quantity of training data to be able to code up this entire mapping, which needs to learn everything from the Poisson stats, the imaging matrix, the system matrix, is all learned here, which is a pro and a con. But then also by using these convolutional mappings, they're only learning 60 million parameters, which, you know, compares favorably. I think I estimated 100 million parameters for one single linear mapping early on. So they've got a parameter reduction, and yet we're still talking a large number of parameters, and so a large amount of training data is needed. And they show, of course, some kind of benefit. They're showing reduced noise in the reconstruction, and of course a direct mapping can give you an inference far, far more quickly than a conventional iterative reconstruction method. Okay, we've got to press on to make sure I get through the content in my limited time. Okay, so there's another method, DPIR-Net, that's Direct PET Image Reconstruction Network. They took that DeepPET architecture that I've just talked you through, and all they did was just add on two components to the loss function. They used a discriminator and they used a perceptual loss. I've described a perceptual loss to you already. With the discriminator, what we're doing there, these are used in GANs. This is trying to learn whether an image is a member of your training set, your training data, or whether it's something else, in other words, something that's been generated or reconstructed. So this discriminator will try and learn whether this looks like a real image, if you like, a proper member of the training set, or whether it looks like something else. And so these two are going to be in opposition to each other, and I haven't got time to go on about generative adversarial networks, but just to point out that we can use the discriminator component in the loss function along with perceptual loss to add to the conventional mean square error loss. We've got a discriminator loss here and a VGG perceptual loss. So by doing that, they get these rather nice images. Now what we're doing is comparing the DeepPET result with conventional reconstruction and conventional kind of post-reconstruction denoising. Their method, using that discriminator and using perceptual loss as well as the mean square error, delivers these, hopefully you can see, improved images compared to the rivals. Maybe it's best seen here, where we're dealing with low count data. So here is the ground truth reference for that. I think this was kind of simulated data, but based on real. And you can see a conventional reconstruction is very noisy. Post-recon, CNN is doing fairly good. DeepPET is doing fairly good, but I think it's only using a mean square error loss. Whereas when they build in their discriminator and perceptual loss, you can see they've got better recovery of, for example, these features here compared to the other methods. If you look at that region of interest, they're doing quite well in their network. So these direct reconstruction methods with suitably chosen loss functions can do a fairly good job. Okay, rapidly moving on. I've really got to accelerate here. This is a well-known Nature paper, 2018, where they basically go from K-space for MR to an MR reconstruction, and here they are learning effectively something like an inverse Fourier transform, although they can handle undersampled K-space here and so deal with that. So this is not going to be as simplistic as an inverse Fourier transform. So we're transforming from that to some latent space representation in the middle here, if you like, and then we can run that through convolutional layers and then arrive at an endpoint image. And they were dealing with 50,000 training data pairs to train up a colossal 800 million parameters. I looked at a paper the other day that said that this network had more than 1 billion parameters. Depends how you read the paper. Anyway, huge number of parameters, large quantities of training data, and yet they got pretty nice results. But there are all kinds of caveats that can be mentioned, and I'll touch on some caveats later on for these direct methods. And so just to report that they had some fairly nice results. They demonstrated it on PET data as well. For me, when I looked at those images, I needed a bit more convincing. I think there are all kinds of things that maybe could be enhanced further. But a nice early piece of work on direct reconstruction, very well known, AUTOMAP. Another method, this is from 2019, operates on CT data. And here, rather than the kind of end-to-end learning, they try and do things in a bit more of a reasoned, principled approach. What they do instead is train the network up bit by bit. So here they're dealing with CT data that could be noisy and could be missing angles. What they do is train up using large amounts of training pairs from simulated data. But first of all, they train up how to denoise, and that's basically mapping from low to high dose, from low count to high count. They learn how to do an effective denoiser in the first part of the first few layers of the network. Then they learn how to fill in missing angles. That's like a kind of in-painting done by deep learning. And then they learn effectively how to do the filtering. So this is quite an extensive few layers here for the analog of a ramp filter. And then finally, I think they do freeze some of the layers here, but they're effectively then learning how to back project and sum those views together. So here, what they did was train up segment by segment, thereby kind of having a more interpretable end-to-end reconstruction where they're training up segment by segment. And that there's obviously appeal in that, because then you can verify that each part of the network is doing exactly what you expect it to do, rather than have this input and that long-distant output and just hope that what goes on in the middle makes sense. Here, it's a bit more principled. And by doing that, they can then get away with fewer training parameters as well. Okay, time is really against me, so direct PET, I'll leave it there for you to look at in the slides. Basically, they're trying to reduce the size of that massive fully connected layer that would be needed for the main, if you like, the in quotes inverse of the radon transform. I can't dwell on this for too much longer, I'm really running out of time. There's also a table of comparison of direct PET reconstruction methods. Key take-home message, they're nearly always operating on 2D data because they're massive networks with huge numbers of parameters, and they often need huge quantities of training data. And rapid example there as well is that of fast PET, where they're using time of flight, most likely annihilation position, histo images, and they just run that through. This is like an image-to-image mapping, basically, but with a UNet type structure where they copy feature maps across at different resolution levels. This seems to be a very effective method. There's the target, there's the reconstructed result. So they've only got 20 million parameters, works for fully 3D, massively faster than OSEM, but of course you're going to make sure you've got to have a time of flight scanner with ability to generate these simple histo images, but seemingly a very powerful approach. So it's published in this year in TRPMS. Okay, I've got to move on. I hope some of those direct methods have been of interest to you, and you would have seen, hopefully I've added some interpretation to them, but I know there are some AI skeptics out there who might view these methods as just discarding physics and picking up a book on kind of, if you like, mindless nonlinear algebra, just do anything, just stir the pile of parameters and hope. Now, some of them can seem that way, although I hope I've motivated what's going on so that it doesn't seem as bad as that graphic implies. That graphic, by the way, is taken from that paper there that I've just recently published with Gail Schramm. But what I'm hoping to convince you of next, I've only got about 25 minutes left, is to say that actually the best thing to do is to kind of do both. You want to get your AI stuff, and then you also want to get your physics embedded in there as well. So if you're an AI disciple, so to speak, and a reconstruction expert, then hopefully this is the picture you will be looking at, where you want to blend these two together, the inverse of the radon transform, as well as AI learning for the bits that we don't know. Okay, so I've got 25 minutes, that's good. Okay, to catch up on now the important final stage I want to go through, which is deep learned iterative image reconstruction.